Class 11th, Subject Physics, 6th chapter, Mechanical Properties of Solids. Mechanical Properties of Solids. From this chapter, let us see elastic modulus. Elastic modulus. We know that there are three different types of stress as well as strain depending upon the change in length, change in volume, or change in shape of the body due to the application of the deforming force or externally applied force. So, as three different types of stress and strain are present there, therefore, three different types of elastic modulus are defined, and these elastic modulus are Young's modulus, bulk modulus, and modulus of rigidity. So let us see first one, that is Young's modulus. So as the elastic modulus are Young's modulus, bulk modulus, and modulus of rigidity, let us consider first Young's modulus denoted by Y. So in order to explain this Young's modulus, let us consider a wire having its original length equal to capital L, which is suspended from a rigid support. At the free end of that wire, a load mg, that is weight mg, is attached. So before applying this load to this wire, the length of the wire is capital L. When it is subjected to this load mg, at that time it will get stretched, that is there is elongation of that wire. Let that elongation is small l. So original length of the wire will be capital L and increase in length of the wire will be equal to small l. Now if you consider this Young's modulus, then we can define Young's modulus with the help of the longitudinal stress and longitudinal strain. That means if there is change in length of the body due to the application of the deforming force, then we can define Young's modulus. Now if we consider the longitudinal stress and longitudinal strain in case of this wire, then we can write longitudinal stress equal to applied force per unit area. That will be written as F upon A. But in this case, the force applied, that is equal to weight mg, and divided by A will be the area of cross section of that wire. If this wire is having its length equal to L and its radius is equal to R, then the area of cross section of this wire will be circular in shape and it will be equal to pi r square, and therefore longitudinal stress will be equal to F upon A, that is mg upon pi r square. Similarly, the longitudinal strain will be equal to change in length per unit original length. Change in length per unit original length. So change in length is small l divided by original length is capital L, and therefore L by L will represent the longitudinal strain. Now Young's modulus of material of this wire is defined as Young's modulus of material of wire is defined as the ratio of longitudinal stress to the longitudinal strain. Young's modulus is defined as the ratio of longitudinal stress to the longitudinal strain, and therefore Young's modulus Y will be equal to longitudinal stress divided by longitudinal strain. But this Y will be then written as this longitudinal stress is mg upon pi r square. So longitudinal stress is mg upon pi r square, and it will be divided by longitudinal strain, that is L by L. So this will be written as this L will be shifted to numerator, that is mgl, and it will be divided by pi r square into small l, and therefore we will get mgl upon pi r square L. So this formula will represent Young's modulus of material of that wire, that is mgl upon pi r square L. Now Young's modulus is defined if that body is having length and there is change in length of that body due to the deforming force, and therefore length is possessed only by the solids, and therefore Young's modulus will be possessed only by the solids. So only solids will possess Young's modulus. Now the SI unit of Young's modulus Y, SI unit of Young's modulus Y will be given as Newton per meter square. It is Newton per meter square, that is force per unit area, and the dimensions of Y will be equal to, dimensions will be written as -1 in length, 1 in mass, -2 in time. -1 in length, 1 in mass, -2 in time are the dimensions of Young's modulus. So this will be the first constant of elasticity or elastic modulus. Now let us consider second, that is bulk modulus, denoted by K, bulk modulus K. If there is change in volume of any object or body due to the application of the deforming force, then we can define bulk modulus. So in order to define bulk modulus, there must be change in volume of the body, and therefore in order to explain this concept of bulk modulus, let us consider a sphere having its original volume as phi. Then the force F will be acting uniformly in all directions on the surface of this sphere directed inwards, so that this sphere will get compressed, that is there will be change in its volume or decrease in its volume, and therefore finally it will take this shape, and hence this will be the outer sphere, this will be the inner sphere. So this is the original sphere and this will be the final sphere, and therefore as original volume is phi, that volume will get reduced or it will get decreased due to the application of the force by an amount d phi. So this will be the portion which is representing the decrease in volume d phi, and therefore if it is the case, then in this case we will define the volume stress and volume strain, and therefore volume stress is given as, volume stress will be equal to applied force per unit area. Volume stress equal to applied force per unit area, that is F upon A. But in this case, this force applied on the surface of the sphere is perpendicular to the surface at each and every point, and therefore as this perpendicular force per unit area represents the change in pressure dP, so that this volume stress F by A will be equal to dP, that is change in pressure. Similarly, volume strain will be given as change in volume per unit original volume, change in volume per unit original volume, that is change in volume upon original volume, that will be equal to, change in volume is dV and it will be divided by original volume phi, and therefore volume strain equal to dV upon phi. Now bulk modulus of material of that sphere will be defined as the ratio of volume stress to the volume strain. Bulk modulus K is defined as the ratio of volume stress to the volume strain, and therefore bulk modulus K will be equal to volume stress upon volume strain. But volume stress is change in pressure dP, it will be divided by volume strain dV upon phi. this phi will be shifted to numerator, and therefore we will get phi dp by dv. Phi dp by dv, that is the bulk modulus. And now, similar to that of Young's modulus, this bulk modulus will be having again the same unit, that is SI unit of K will be given as Newton per meter square, and similarly dimensions of K will be again -1 in length, 1 in mass, -2 in time. -1 in length, 1 in mass, -2 in time. And for solids as well as liquids as well as gases, it will possess the volume, and therefore we can say that as volume is possessed by all the solids, liquids and gases, therefore bulk modulus will be possessed by the solids, liquids and gases. So only bulk modulus will be possessed by all the states of matter, that is solids, liquids and gases, because all these states are having their own volume. Now, the reciprocal of bulk modulus is called as compressibility. The reciprocal of bulk modulus is called as compressibility, and therefore compressibility equal to 1 upon bulk modulus. 1 upon bulk modulus, that is reciprocal of bulk modulus, is called as compressibility. Again, its SI unit will be meter square per Newton, and the dimensions will be 1 in length, -1 in mass and 2 in time. 1 in length, -1 in mass and 2 in time. And now let us see the third elastic constant, that is elastic modulus, and it is modulus of rigidity. Modulus of rigidity denoted by eta. Modulus of rigidity eta. Modulus of rigidity eta. So if there is change in shape of any body due to the application of deforming force, then we can define the modulus of rigidity. So in order to explain this concept of modulus of rigidity, let us consider a cube which is made up of different layers. The bottom layer of this cube will be kept fixed, and the upper layers will be loosely connected with this bottom layer. Now let L be the length of this cube, and each surface of this cube will be having its surface area equal to A. Now the force F will be tangentially applied on this upper layer, so that this layer will get displaced in the forward direction with respect to this bottom layer. Because this bottom layer is at rest, it will be fixed, so that only there will be displacement of this upper layer, and therefore due to the displacement, that is lateral displacement of this layer of that cube, there will be change in shape of the cube, and therefore we can define modulus of rigidity in this case. So in this case, as there is change in shape, therefore shearing stress will be equal to applied force per unit area, that is F by A. Applied force per unit area, that is equal to F by A. Then shearing strain will be equal to simply theta. Shearing strain equal to theta, and therefore the modulus of rigidity is defined as the ratio of shearing stress to the shearing strain. The ratio of shearing stress to the shearing strain is called as modulus of rigidity eta, and therefore modulus of rigidity eta equal to shearing stress upon shearing strain. Shearing stress upon shearing strain, and therefore we can write eta is equal to F upon A upon theta, that is equal to F upon A theta. F upon A theta. Now in this case, the shape is possessed only by the solids, and therefore modulus of rigidity will be possessed only by the solids. Again, SI unit of this modulus of rigidity will be similar to that of Young's modulus, that is Newton per meter square. Newton per meter square, and its dimensions will be again same, that is -1 in length, 1 in mass, -2 in time. -1 in length, 1 in mass, -2 in time. So this will be all regarding the elastic modulus, that is Young's modulus, bulk modulus, and modulus of rigidity.